Hi there, my name is Dr. David Redpath, and I'm going to be speaking today about our project DART, Detect and Avoid Artificial Reality Test. This was work done under the DTrig drones program. I think most of us in the drone industry are aware of the opportunities we have in the future for beyond visual line of sight drones, but also a little bit we're all aware of maybe the regulatory barriers or issues that we need to address to be able to get where we want to be in the future. In terms of challenges, I think a lot of this really comes down to autonomy that these drone systems need to have, which is what a lot of the exciting DTrig drone projects we're looking at in 2021. There was a couple of documents that the CA released, CAP 1861-61A, that looked at beyond visual line of sight drone operations and detect and avoid ecosystem. Really this has been used in a lot of robotics verticals, this idea of trustworthy autonomous systems, and this is where our project DART came in, of building a simulator for detect and avoid algorithms. The CA document 1861A, there was a good section in there that really looked at this problem of looking at detect and avoid algorithms, that how do we test something like that in a repeatable fashion. It's not easy to go out to an airfield and deliberately try and fly our drone into manned aviation. So really this is something that we want to be putting into a kind of simulation scenario. Also another objective of DTrig when we started was that this strictly wasn't supposed to just be simulation of theoretical scenarios, it needed to be as real as possible. So a big part of our project was about using hardware in loop as much as possible. So our innovation for DART, there was quite a lot of enabling technologies that already existed. When we first looked at this project, we'd been back in 2020. We had an idea to build something using a games engine, and this is maybe what brought our first interaction with our partners at the University of Edinburgh. And really one of the academics there made us aware of a program from Microsoft called AirSim. And that was really a bit of a kind of suite of tools based on Unreal Engine 4 that has a kind of virtual drone that you can then maneuver around a kind of a simulated environment which you build up within a games engine, a bit like how you would build a computer game. So really this had at least 80% of the technology that we required to begin. However, there was still quite a lot of functionality to be able to build kind of collision scenarios that we wanted to do in quite an open way, because one feature of AirSim which makes it quite attractive is it works on Windows and Linux operating systems, and you've also got the option, it doesn't necessarily need to be on the Unreal Engine games engine, it can also work on a Unity system. So this gives you a little bit of flexibility if you want to bring in contractors from the games industry to really build you, a real digital twin of whatever the kind of con-op situation that you might want to be flying your drone in. Again, I mentioned already about a big part of our project was about getting hardware in the loop as much as possible, and AirSim made this quite easy, along with the PX4 Pixhawk system that runs on a lot of kind of open source kind of drone technology now. So most of this was all possible to do in configuration files, though it did take us a couple of weeks to get our system up and running. Again, the major objective of our project was to build a simulator, but first thing, obviously, we needed to detect and avoid algorithms to test with, and obviously a lot of this is all hidden within, we're not pretending that we're first to do this. A lot of big companies have detect and avoid algorithms, zero of which is in the public domain. So again, we needed to go and get some of our own research done with the University of Edinburgh. But one of the kind of deliverables we set with them is we needed, we didn't want to be writing code for months on end in C++ and writing our own libraries. We needed to, be using building blocks to do this, that, we could give this code to other investigators and they could get something up and running in kind of days and weeks rather than months. So we can set them the task of looking for relevant OpenCV functions that could be used with Python to write these algorithms. There are a lot of ways that you can look at the detect and avoid problem using, say, radar and a million other technologies. But we really wanted to make this as simple as possible. So another thing that we kind of set up was this kind of need to use a monocular camera only, because a lot of drones have small cameras available. So that was a particular set of kind of circumstances that we set up to do this. First part of our research, in building a simulator for doing these kind of benchmark tests on, that you really need to consider all the kind of issues that might well be involved in how to evaluate this. So we spent a couple of weeks, going through, really just making a very long list of, what sort of situations drones that are flying and looking to do a kind of detect and avoid scenario, what sort of criteria would be involved in, stopping a successful detection, things like going behind terrain, getting dirt on the camera lens, moisture, weather, things like that, really just making quite a long exhaustive list, because these are the inputs that need to go into the simulator to exhaustively test these algorithms. It's worth noting that this document is online, and there's a URL there which takes you to one of our Teams folders that has that document. All our work is open to the community. We're really looking for other businesses, academic partners to contribute to this as well, so it can be a bit of a kind of open document to start building up information. So it's there online on that URL. Please take a look at it if you wish to contribute. My email will be at the end of the presentation. The second part of our project was to go about building the simulator. Again, there wasn't anything too in-depth here. We maybe wrote about 1,000 lines of code in Python and a few scripts, but really the key element for us was how to get the kind of video camera streams out of Unreal Engine and to consume those with the OpenCV algorithms in order to issue the detect and avoid result. So you see an example screenshot here of one of the detect and avoid scenarios where we have a Cessna here on a collision course with a small drone. The camera feed, which you'll see in a later slide, you'll see the kind of head-on shot of the Cessna approaching. We use a Cessna here, but there was a few different models that we used. 747 aircraft, helicopters, other drones. Those are some of the kind of scenarios that we threw into the mix. It's worth noting as well that a big part of our project, obviously being able to do this type of work, is we did need a bit of reasonable horsepower to be able to run these simulations in a repetitive manner. Maybe another thing worth mentioning was that the way that the simulator was written is it was real time, which was good for hardware and loop testing, that everything was running in real time, but there might be some scenarios where you might want to run this faster than real time if you wanted to do, say, parallel simulations and do these millions of times on really high performance computer. Then this might not necessarily be the right format to do that. This just another slide here talking a little bit about hardware and loop. We started doing our work as software and loop predominantly, which when I say that, it's nothing more difficult than just a piece of code running on the same computer as the simulator. We did step this out though, setting up a Raspberry Pi as a mission computer and then streaming the output from the Unreal Engine just over Wi-Fi to the Raspberry Pi, so the Raspberry Pi could then issue the detect and avoid instructions to the flight controller. Again, probably seems like a bit of a chicken and egg scenario, building a simulator without any algorithms, but I was going to speak a little bit about the algorithms that we developed. This was research performed by the University of Edinburgh, just based around our criteria of being able to build to detect and avoid algorithms quite quickly using OpenCV. So the two methods that they researched for us and suggested was an optical flow based method and a tracking based method. So for the first method and the first algorithm we used for optical flow, this is essentially just looking at a grid of, if you can imagine a small series of squares, a grid across an image, and you're then comparing subsequent frames and looking for shift in the pixels. This allows you to create an optical flow field that you can see in the top picture there, basically a series of kind of vectors, arrows, looking at how things are moving through the image. And certainly the academic work there suggested we just use the global sum of this vector field to suggest that there might be something moving towards us, and then to issue the avoid algorithm in obviously the opposite direction. The second algorithm they suggested was tracking. There's quite a few off-the-shelf trackers available in OpenCV, which allows you to do things like kind of face tracking, things like that. However, the first thing that the tracker algorithm needed was to issue a region of interest, a square of something that you wanted to track. So this gave us a little bit of problems because essentially the academic research didn't provide a method to do that. However, I did manage to find just a simple frame subtraction algorithm which shows that there's something moving within a frame that you can then draw the region of interest or the kind of bounding box around to then input to start the tracker. So that was algorithm 2. So the results from using our benchmarking suite on these two detect and avoid algorithms was that we used quite specific scenarios. We didn't use a lot of clutter in the scene because we know that these basic algorithms would have failed. In the majority of situations, a drone or aircraft is going to be quite high up in the sky, so we weren't going to try and make, take baby steps essentially in testing these before we added more difficulties. The main issue we found certainly with optical flow, which caused a failure, was it was very sensitive to global movement. So it's essentially if the drone camera was kind of rocking from side to side, that would trigger a false alarm. The tracking method was a little bit more robust because that was looking at smaller regions of interest within the frame. Another thing was when we did the simulations, we looked at different collision courses towards the kind of reference drone. So we did notice that both algorithms were more sensitive to issuing a successful detection when things moved across the frame transversely, as opposed to when the simulated aircraft was moving at it directly. And just to conclude, really this project, we weren't trying to solve the detect and avoid algorithm. This was really the scope of this project in the short timescale to do it in. This was really just trying to lay foundations for what we hope can be an open test framework for the evaluation of detect and avoid algorithms. We certainly think it ticks the box that the CA are asking for an evidence framework to show that detect and avoid algorithms are trustworthy. We have our initial benchmarks. All this work will be published on GitHub for other researchers and businesses. Are welcome to download the code and set this up themselves. We certainly hope that it's our major objective in this project was to kind of build a bit of a community around this and keep adding to the DART framework, so that other universities and businesses, we can all collaborate on building this kind of package of standards up to evaluate our individual detect and avoid algorithms. That's a major objective we hope that this project can reach. So I'll just finish by leaving my contact details. I'm welcome for anyone that's got any questions on this to reach out, and I'd be welcome to offer what information I can about the project. Thank you all.